Pretty sure.
Let's see if I can stop sneezing here. So a lot of what's coming up in the next couple of lectures is going to be really theoretical and concept-based. There's a little bit of actual math in it, but it's mostly theoretical, and you're going to sort of have to try and do the best you can with this, because a lot of it's really hard. Okay, so last time we talked about this idea that we found out that although most physicists thought that when something emits electromagnetic radiation, remember, we're made up of atoms, and the gazillions of atoms that we have are constantly raising and lowering their energy states. And when you lower your energy state, the energy state of an electron, an electromagnetic wave is given off. And this may not seem like a lot. And the other aspect of that that's a little bit confusing is we're not just emitting radiation, right? We're also absorbing radiation. If we just emitted radiation, we'd run out of energy after a while, right? But we're also absorbing radiation from the environment as well. And so our atoms are constantly both absorbing energy and giving energy back off. And we're basically glowing, right? We're basically glowing. It's just that nobody can see our glow because that radiation that we're giving off isn't in the visible light range. It's mostly in the what range?
Ultraviolet? No.
Infrared. Infrared. Yeah, most of our radiation that we're giving off is in the infrared range, right? And we talked about this type of radiation called black body radiation. Physicists thought would just simply represent changes in the energy of motion of the particles. But they made some observations that made them think that we don't just have a loss of energy when particles change motion, but they couldn't figure out what was going on until Planck came along in the early 1900s and figured out that the energy that we radiate also included a loss of potential energy, not just a loss of kinetic energy. And the thing that bothered them about what they found out was that the energy was quantized. Okay, and that's the real confusing part about all this. We would think that if we're changing energy, we could change any energy we wanted to, right? We could lose a certain amount of energy or a little bit less energy or a little bit less. But no, we found out that we could only change amounts of energy by certain amounts. And that these certain amounts of energy corresponded to wavelengths of the electromagnetic spectrum, and that we could actually figure out how much energy each quantum or each wavelength was responsible for. And this ultimately led to the discovery that at the atomic level, because of the distances involved, the fact that we're at billions of meters rather than visible numbers of meters, objects at that size travel or move or gain or lose energy more related to wave motion than they do to translational motion or motion in a straight line. So again, a lot of this will become more clear when we get a little bit deeper into this. But we at least should know that when we have an electromagnetic wave released from an atom, we can figure out how much energy that's released. The amount of energy that's released is related to Planck's constant times the wavelength, right? Or we said that that was going to be Planck's constant times c over
C over nu. I'm sorry, yeah, C over lambda. No, C over nu. If I could just go up, C over lambda. Okay, so I got those backwards, didn't I? So Planck's constant times the frequency, or Planck's constant times C over the wavelength. Think about it in that way. But anyway, there was some additional pieces of information that came along that couldn't be explained by traditional physics, and only when we started thinking about the idea that we have these things that we're calling waves, that we have energy, that has energy in them, these things that have these waves that have energy in them, that also have features of particles, which is an odd thing, and it's called the wave-particle duality. We started to be able to figure these things out. There's another thing that we have called the photoelectric effect, another important piece of information that led Einstein to add support to the particle nature of electromagnetic radiation. Scientists were initially skeptical of Planck's vision of energy as being quantized, and he wasn't formally recognized for his amazing leap of intuition until 1918, when he won the Nobel Prize for it. It took Albert Einstein to describe something called the photoelectric effect to really convince them. Like black body radiation, this was another phenomenon for which classical physics had been unable to provide an explanation. And again, your level of understanding just simply needs to be that classical physics couldn't explain our observations, okay? You're not going to have to get too deep into the explanation here. You just need to know that classical physics couldn't provide an explanation for the fact that waves were starting to appear like they had a particle nature. But the photoelectric effect is a phenomenon in which if electromagnetic radiation of a frequency above a certain threshold is directed at a piece of metal, so if I've got a piece of metal here, and I direct an electromagnetic wave at it, okay, electrons will flow from the metal. Okay, so in other words, if I direct electromagnetic radiation at this piece of metal, and I've got this hooked up to some kind of a circuit, I'll be able to see that electricity flows through the circuit if I direct wavelengths of certain types at this metal. Okay, and the criterion was that this electromagnetic radiation had to be above a certain frequency threshold. In other words, it had to supply a certain amount of what? If I'm talking about frequency, I'm thinking about
Wavelengths.
energy, right? Okay, so if I want to cause these electrons to flow, the implication here is that if I have to be above a certain frequency, I have to supply a certain amount of energy. And for our understanding, that makes a little bit of sense, right? Because if I'm going to cause electrons to flow from this, I'm going to have to kick the electrons out of their energy levels. I'm going to have to remove them completely from their atoms. And we were just finding out about electrons and protons. We didn't have a good understanding of that yet, so this was a little bit difficult. But there was a conflict with classical physics. This threshold frequency, scientists of the time assumed that energy added associated with a wave depended on its amplitude, not its frequency. What do we mean by amplitude?
Is that the wave? No.
The height?
The height. So if I have this wave up here versus this wave, this one has the greater amplitude, right?
Yeah.
Okay, so the strength of the wave, not the frequency of the wave, but the strength of the wave. And they still didn't really quite get this at the time. So scientists of the time assumed that the energy associated with a wave depended on its amplitude, not its frequency. the more intense the electromagnetic radiation, the greater this effect should be, which is what they thought. They also thought if the source of electromagnetic radiation was weak enough, or just weak, it should take a while to absorb enough of it before electrons would flow from the metal. So they thought there should be some kind of a cumulative effect. So if I have a weaker source of electromagnetic radiation, there's not quite as much strength to it. Well, let's just beam it onto this metal for a period of time and I'll start to get electrons flowing. But they predicted it would not make any difference what the frequency of the radiation was. It should only depend on the intensity. However, investigations showed that there was, in fact, a threshold frequency below which it didn't matter how intense the radiation was. The photoelectric effect didn't occur. So if I was below a certain frequency of radiation, I could make it as intense as I wanted to, and I wouldn't get any electrons flowing from this. Further, above this frequency, it didn't matter what the intensity was either. The photoelectric effect still occurred. So I could have a really, really weak electromagnetic radiation above this frequency, and it would still cause this photoelectric effect to occur. There's also something called lag time. Scientists of the time also assumed that depending on the intensity, there may be a lag time before electrons started to flow. The dimmer the electromagnetic radiation, the longer it was before the metal should absorb enough energy before electrons could be released. However, investigations revealed that no matter how dim the radiation was, above the frequency threshold, electrons started flowing immediately. Okay, so if you think of let's say a brick. If you think of a brick sitting on a shelf here, and you want to knock it off the shelf. Okay, you want to knock it off the shelf. If you throw a baseball at it, okay, and we're going to say the baseball represents a high enough frequency. If you throw a baseball at it, it doesn't really matter how hard you throw the baseball. Even if you just shove it a little bit right in front of it, you're for most intensities, you're going to be able to knock the brick off the board, right? But if you throw a ping pong ball at it, it doesn't matter how hard you throw the ping pong ball, you're not going to knock this brick off the shelf. Okay, so that's what this idea is. The idea of frequency being the thing that's imparting the energy to this. So if I have something above a certain frequency, it doesn't really matter how hard I throw the baseball. And that falls apart a little bit if I'm just kind of shoving it up against there. But it doesn't really matter how hard I'm throwing it. If it hits the brick, it's going to knock it off. But if I throw a ping pong ball, it doesn't matter how hard I throw it. It doesn't matter what the intensity is if I'm below that frequency. So that's kind of a way to look at the photoelectric effect. The problem with the wave theory was that it assumed that the energy transmitted by the wave is equally distributed throughout the wave in the changing of its electric and magnetic fields. It did not occur to anyone until it was proposed by Planck that the energy of the wave might be concentrated into a particle-like packet of energy. And again, the fact that something was incremented or quantized implied that there was a particle nature to this. And that was the thing that everyone was all freaked out about. No, it's a wave, right? It's a wave, and the energy is distributed evenly throughout the wave. Well, no, it's not. The energy of the wave is condensed into a small particle-like packet of energy called a photon. And in 1905, Albert Einstein, based on Planck's idea that energy was quantized, first proposed that the energy of the wave was, in fact, packeted or packaged in this quantum or photon of energy packet. So most importantly, Einstein suggested that an atom can only change its energy in discrete amounts by absorption or emission of a photon. So the idea being that if I have an electron here in motion around the nucleus, I can only absorb an amount of energy that's going to get me up to this next level. If my packet, or if whatever this photon delivered to me is not great enough to get me to that next level, I can't go to that next level. Okay? It's not allowed because it would screw up the wave motion of my electron to move it to here. Okay, if I had a certain amount of energy that was added to that wave motion of that electron and it moved it up to this amount of energy, that particular wave that represented that particular energy would be destructive to the other waves of the other electrons around it. Only if I kick it up to here will it be consistent with and constructively interfere with the other waves. Okay, so we can't do that. Now we can certainly add enough energy to get it to the next level, and if there's some extra energy left over, then that extra energy might go to increasing the motion of something, maybe the whole atom itself. But I can't use any less than that. Okay, I can only use the amount of energy that gets me up to there. So to set the stage for the development of our understanding that the photon added or lost from an atom caused a change in potential energy reflected by a change in the wave motion of an electron. A change that wouldn't happen unless the addition or loss of energy change caused the wave motion to an allowed frequency. If electromagnetic radiation caused electrons to be released from a metal, now at some point, if I had enough energy, if I had a high enough frequency, I'm going to kick this past the second energy level, past the third energy level, past the fourth energy level, past the fifth energy level. I'm going to kick it past all of the energy levels, and I'm going to cause the electron to be completely released from the atom. Okay, and that's what was going on here. If electromagnetic radiation causes electrons to be released from a metal and the energy of the photon striking the metal is greater than the energy required, what happens to the extra energy? Well, the rest of that energy is going to go to increase the motion of that electron. Okay? I'm going to change the potential energy until I kick it out of the electron. But once I kick it out of the atom, the rest of the energy is going to go to increasing the motion of the electron. So whatever its motion is, now it's not going to be bound to the atom. It's not going to be constrained to a wave motion that's part of the atom. It's going to be moving in a linear pattern. Okay, once I kick it out of there, it's not going to be moving or constrained to that motion anymore. So I can add to its translational motion or its linear motion, and this extra energy. So whatever the energy of the photon was, minus the amount of energy required to release this electron, is going to be added to the motion of the electron, how fast it's going. Okay? So that's another piece of evidence here. That's called the photoelectric effect. Okay? So we need to then talk about an idea called mass energy equivalence. Can I get someone to shut that door for me? So Einstein provided one of the last pieces of information necessary to the concept that energy and things that travel as waves also have features of a particle. And that's where all this was headed, right? We had the idea that energy was quantized. Okay, we had the idea that energy was quantized, and the fact that it was quantized, as well as the photoelectric effect, suggested that electromagnetic radiation has a particle nature. Okay, they even called the particle a photon. Okay, and Einstein provided one of the last pieces of information necessary for this to become a real thing and for everybody to accept it. Now, I want you to look at these various formulas for how we quantify energy. Okay, 1/2 mv squared is the amount of what type of energy? Kinetic energy. Okay, the formula for potential energy, gravitational potential energy, is mgh. Another formula, and this one's basically for work, which is also associated with energy. So mass times the square of the velocity, mass times the gravitational acceleration times the height, mass times acceleration times the distance traveled. All of these are equivalents to energy. And it should strike you that this is kind of strange, because what is the constant component of all three formulas? Mass. Okay? Energy equals mass times something. Okay? People hadn't really thought about this in this way before. Energy equals mass times something. In all of these situations, mass is a component. In fact, in all of these situations, you can picture the formula as if energy equals mass times something else, like mass times some type of a constant. What if energy and mass are truly equivalent aspects of the same phenomenon? Okay? What if mass and energy are basically the same thing, or very similar in nature? The idea that mass and energy are equivalent is a concept called mass-energy equivalence. In this concept, mass is considered to be a property of all energy, and energy is considered to be a property of all mass. As with many other physical relationships, energy and mass are seen to be connected by a constant. Since we know that units of energy are joules, and joules break down into kilogram meter squared per second squared, and let me show you that. I think I've shown you that one other time. But if I know that joules also equals something called Newton meters, okay, and I know that newtons are our unit of force, right? And I know that force equals mass times acceleration, and I know that mass is kilograms, and I know that acceleration is meters per second squared. I increase my velocity by so many meters every second, right? Kilogram meters per second squared. And I take that and multiply that times meters. I get kilograms times meters squared per second squared, which is what a joule is. Okay? So since we know that the units of energy are joules, which break down into kilogram meters squared per second squared, and we know that mass is the kilogram part of this, right? Mass is the kilogram part of this. What units would this constant need to make mass equivalent to energy? What units would this constant need to make mass equivalent to energy? And we should recognize that ms, or m squared over s squared, would be the same thing as what else squared? What if I did this? okay, and change this into that, what's meters per second?
Per second is, that's a wavelength? No.
What's meters per second? It's velocity, right? Meters per second is velocity. So meters squared per second squared would be the same thing as what squared? Velocity squared. What velocity are we probably referring to here?
The individual particles in the wave.
Okay, but yeah, the speed of light.
Oh, yeah.
Okay, so speed of light. So c, which is the speed of light. Okay, so it really isn't that much of a leap for Einstein to get to this. If you understand physics this way, okay, if you understand that every formula I have for the quantifying of energy contains mass, and then the other part of it always goes to meters squared per second squared, right? V is meters per second squared. G is meters per second squared. And H is meters. And then acceleration is meters per second squared. And distance is meters. Everything I've got here is mass times velocity squared. It's not that big of a leap for Einstein to create this equation that says energy equals mass times the square of the speed of light. And this is the energy of electromagnetic radiation we're talking about here, right? So, except there's a problem. Waves don't have what?
Mass.
Okay, so if I'm saying E equals mc squared and I'm referring to electromagnetic radiation, but at the same time, electromagnetic radiation doesn't have mass, I've got a huge problem. Okay, so for our purposes with this idea that energy and mass are equivalent, or that energy is simply mass times a constant, Einstein formalized this in 1905 in his famous equation. And it's not really just electromagnetic radiation here, it's anything that we're talking about. Einstein actually came to this equation by considering the relationship between space and time, how time passes for someone in motion compared to how time passes for someone observing the person in motion. And it's not actually the same. Fortunately, we don't need to figure that out for this. We only need to understand the relationship between energy and mass. So here's an illustration of what happens. During the breakdown of 1 kilogram of uranium-235, uranium has what feature, what property?
Radioactive.
It's radioactive, right? It breaks down. So during the breakdown of 1 kilogram of this, 6.7 times 10 to the 10th joules of energy is released. That's an enormous amount of energy, right? Okay, that's 67 billion joules of energy released during the breakdown of 1 kilogram of uranium. Okay, if we say that the release of this energy was the result of the conversion of mass to energy, we could predict the amount of mass we would expect to lose as a result of this conversion. So we need to get used to this idea that mass and energy is the same thing. They're the same thing, and I can convert mass into energy or energy into mass. Okay? And if I wanted to find out how much mass I would lose in this breakdown by converting it to energy, that's what we did, right? I'm converting a certain amount of mass into a certain amount of energy. I would say that mass equals the energy divided by the speed of light. So here's the amount of energy. Here's the speed of light squared. And we would predict that out of this 1 kilogram, we would lose 0.0000074 kilograms of mass. Okay? Now, that may not seem like a tiny amount of mass, but think about that. How extraordinary is that for a 10 billionth of a kilogram of mass to be converted into that much energy? And this is in fact what occurs. If we measure this amount of mass, we find out that we lose that amount of mass. So we literally can turn mass into energy and energy back into mass. Now, again, here's the problem. If we're suggesting that waves behave like particles, but the particle that we're talking about, the photon, has no mass, how can we make a connection between the particle nature of a wave and its energy? Okay, if I don't have mass in my photon, how can I possibly hope to equate it to an amount of energy? Mathematically, we can make this connection by saying that even though the particle does not have mass, it has a property of mass called momentum. Momentum is an amount of motion. And the way that I like to illustrate it in physics is by talking about track trains. If we have a track train that's going 30 meters per second, and we have a bicycle that's going 30 meters per second, they're both going the same velocity, right? Okay? But which would you rather get hit by? A track train going 30 meters per second or a bicycle?
Bicycle.
Bicycle, right? Because there's not nearly as much motion associated with that as there is with the track train. Momentum is a quantity of motion. How much motion does this have? And we talk about momentum in terms of mass times the velocity. So if you consider the mass of the track train, it's hugely greater than the mass of the bicycle. So the amount of energy that the amount of motion that track train has is much greater than the amount of motion that that bicycle has, even though they're traveling at the same velocity. Okay, so momentum is a concept that adds into the mix the amount of mass. So classical physics symbolizes momentum with the symbol P, not sure why, and states that a particle's momentum is equal to mass times its velocity. Again, this doesn't seem to help us much because a photon of energy doesn't have mass, and this momentum formula requires mass. But now that Einstein had connected energy and mass in this way, how might I resolve our mass issue? If I know that E equals mc squared, what might I do to take mass out of this equation?
Could you do P equals E over C squared V?
Okay, and that requires me doing what with mass? Saying that it's equal to P over V, right? And then substituting that in for mass. And that's going to be then E equals P over V times C squared. Okay, recognizing that these are both velocity terms, I've got one above and one below the denominator. That would mean that energy equals momentum times C, right? Because that and the square are going to drop out. Okay? Now, is there something else related to waves that we're aware of that energy is also equal to? We just used that last time to find the energy of a certain frequency of light. Remember, energy equals Planck's constant times the frequency of that radiation, right? So I could also say that that's equal to h times c over lambda. And I could substitute this in for energy. And so I could get h times c over lambda equals momentum times c. And how can I simplify this now? Or actually, let's do it with this first. So let's say HV or H nu equals PC, and we'll put an intermediate step in here. Now recognize that V over C is the inverse of C over V, which is the same thing as lambda. So V over C equals 1 over lambda. And if I change this to H nu over C equals momentum, then this equals 1 over lambda. So we have H over lambda equals momentum. Okay, which is what we could have done that way. So I got to that by two different ways, didn't I? I could have just done this directly by substituting C over lambda in here, but I could have also done this by dividing both sides of this by C and saying nu over lambda is the same, or nu over C is the same thing as 1 over lambda. In any case, we get the fact that momentum equals the Planck's constant divided by the wavelength. So even though a photon does not have mass, it does have momentum. Okay, which is weird, you just have to accept it, right? Momentum is a property of a particle. Even though the classical physics formula momentum equals mass times velocity includes mass, we can show that if we assume mass energy equivalence, all right, that's what Einstein brought to us, right? He said mass and energy are equivalent. If we assume mass energy equivalence, momentum of the photon equals Planck's constant divided by the wavelength. So a wave can have some features of a particle. The momentum depends on the wavelength and thus on the frequency of energy, all of which are limited by the restriction of having to form something called a standing wave. In this way, momentum can be seen as the connection between energy and mass and the wave-particle duality of matter and energy. Now, I have no idea what I meant here by saying wanting to do the same thing for mass. My brain isn't connecting with why I put that there, so I'm going to hold off on that. But I want you to understand we've shown fairly conclusively that by saying momentum equals Planck's constant divided by the wavelength, we've shown fairly conclusively that waves have particle natures. Okay? And that's a big part of our understanding in all of this. What Planck brought all of us to was the understanding that waves have particle natures. Okay? But that's only part of it. Okay? Now, if a theory is true, we should be able to make predictions that can be tested which support the theory. If photons have a particle nature and thus have momentum, and if the momentum of a photon is Planck's constant over the wavelength, what should happen to the wavelength if the momentum of a particle is decreased? So if I've got momentum equals h over lambda, what should happen to the wavelength of an electromagnetic wave if I decrease the momentum? What's going to happen to the wavelength?
It should get longer.
It's an increase, right? It's an inverse relationship. If I decrease the momentum, okay, I should increase the wavelength. And so a very clever gentleman named Alfred Compton created an experiment to test this. 1923, Alfred Compton directed X-rays of a particular wavelength at a sample of graphite, which is just carbon. So it's got a sheet of carbon here, and he directed X-rays at it. Okay. According to the developing theory of the particle nature of electromagnetic radiation, if any of the X-rays energy was absorbed by hitting electrons of the atoms of the sample, the photon hitting the electron should lose momentum. That makes sense, right? If my wave has a particle nature and it smacks another electron and imparts some energy to that electron, according to this, the wavelength of the light that's going past that should increase. Okay? The wavelength of the photon after hitting the electron should be longer. And this is, in fact, what happened. So if I remember that I've got gamma rays and then X-rays and then UV rays and then visible light and infrared and then microwaves and then radio waves. Okay, there's my spectrum. If I smack an electron with an X-ray and the wavelength gets longer and the wave comes out the other side of that little sheet of graphite, what should the wavelength, where should that end up in the spectrum? Below X-rays or above X-rays? As far as wavelength goes. Which way am I increasing the length of wavelengths? To the left or to the right?
Increasing wavelength is to the left.
Yep. Okay. So whatever comes out of here, the wavelengths of that electromagnetic radiation should be below X-rays. And that's, in fact, what happened. And that's called the Compton effect. The loss of, or the increase of wavelength in a photon that loses energy because it interacts with some other type of particle that can suck energy out of it. Okay? Okay, so pretty conclusive evidence. And one of the things that you might be asked related to this stuff on the AP test would be in multiple choice questions. Provide an understanding of evidence that waves have a particle nature. Okay, so things that would be considered as evidence of waves having a particle nature, the photoelectric effect, the Compton effect, and the fact that waves have momentum. Okay, so those would be pieces of information that might be listed out in a multiple choice question that would test your understanding of that. How do we know that waves have a particle nature? Okay, those pieces of information.
How many questions are there usually on the test?
So we'll talk about the test after Christmas. We'll talk about the makeup of the test, the number of and we're not 100% sure how it's going to look given COVID. I mean, it was changed last year because of the need to scale back the amount of information that you were supposed to have known.
So basically made it easier.
Yeah.
Yeah, but
Well, easier and harder.
it was easier, and so that was nice because everyone knew what they were doing, but because everyone knew what they were doing, and since it's graded on a curve, it made it so a lot of people got a lot lower scores than they felt like they should have.
Oh,
So like, I didn't pass the AP World Test last year, and the entire class like knew exactly what we were doing. But I was this close, and I got a 2, just barely, because everybody did really good. So, yeah, something to keep in mind.
Well, the other thing is that although the problems will require a little bit less knowledge, they'll require a greater skill at application.
Yeah.
So you won't have to know quite as much, but you'll have to be able to apply what you do know with greater skill.
alright.
Okay? But we don't know how that's going to work out this year. So we've shown that physics finally figured out that energy waves had a particle nature based on the fact that energy appeared to be quantized. We said that Planck's discovery of a quantum of energy through identifying the requirement for radiation emitted to be quantized. He found that out through his understanding of blackbody radiation. Einstein's confirmation of this concept based on his explanation of the photoelectric effect and the use of the term photon. Einstein's statement of mass energy equivalence, allowing us to show that photons have momentum, and then the Compton effect. These are the 4 pieces of evidence that waves have a particle nature. Okay? But this still doesn't tell us why energy is quantized. It just says that it's quantized. It doesn't say why it's quantized. Why is energy quantized? What is it about the nature of the atom that requires me to jump from one level of energy to another level of energy instead of having a continuous increase? Consider one other fact about the proposed nature of atomic structure that did not make sense to physicists of the early 1900s. It was known at the time that if a charged particle was in motion and its motion changed, electromagnetic energy was released. In fact, this is how we create electromagnetic energy of certain frequencies for things like communications. We cause charged particles like electrons to move back and forth in an electrical circuit, constantly changing their velocity. Okay, if I make an electron go back and forth in an electrical circuit, okay, it's going back and forth. As it approaches this area here, it's got to slow down. As it goes back the other way, it's going to speed up, and then it's going to slow down again, and then it's going to stop and come back. It's never actually going to quite stop, but it's going to keep going back and forth, and it's going to be constantly changing its motion. Okay? And by that I mean it's constantly changing its velocity. Okay, it's constantly changing its velocity, and sometimes it changes its direction as well. So it's changing its motion. And as the motion changes, electromagnetic energy is released. If electrons were in motion around the nucleus of the atom, as their motion would constantly be changing, they should be constantly emitting electromagnetic radiation. Right? If I have, even if I don't know exactly how it's moving around the electron, or around the nucleus, if I have an electron that's moving around the nucleus here, it's constantly changing its motion. And this thing should constantly be emitting electromagnetic radiation because they thought the motion of this particle was in some way through two-dimensional space. They didn't realize it was in the form of a wave. They thought it was just motion of the particle through space. In fact, they thought it was actually in orbit for a while around the proton. Now, the problem with that is if the electrons are constantly emitting electromagnetic radiation, they're losing energy, and as they're moving around the nucleus, what should happen to them eventually after I lose enough energy? I've got a positive charge in the nucleus and I've got a negative charge on the electron. And the electron, the only reason it's not collapsing into the nucleus is because of its
its energy, but if I'm losing that energy, what should happen to the electron? It should collapse into the nucleus, right? Should collapse into nucleus. And that wasn't something physicists of the time could explain. Why doesn't if this is how you say it is, if this electron is constantly emitting electromagnetic radiation as you say it is, why aren't my electrons constantly collapsing into the nucleus and destroying the atoms? Okay, so people started to get this idea that electrons as particles could not be in motion around the nucleus in the way that it made sense for them to be in motion, because this would mean they should constantly be losing energy, which would cause them to fall into the nucleus. Further, because energy can only be added or lost from atoms in certain amounts, this must mean that whatever the motion of the electron is, it must be constrained in some way to only allow certain motions. Okay? Not only is my electron not able to move around the nucleus in a conventional way, it has to be constrained, because each energy level should represent one type of motion, another type of motion, another type of motion. It's constrained in some way to only allow certain motions. So a French physics student named Louis de Broglie decided that electrons must be constrained to wave motions that produce something called standing waves. And we're going to talk about this here in just a second. Okay? In the 1920s, French physics students Louis de Broglie asked the right question. If light, which we think of as being a wave, can have a particle nature, does this mean that particles can also have features of waves? De Broglie thought about systems in which, because of the constraints of the system, only certain motions could occur. The main system that he was aware of that was confined to certain patterns of motion because of the physical constraints of the system was a system involving the production of standing waves. So we need to make sure we understand what that is. Okay? We need to make sure we understand why the motion of an electron as a wave would make it so only certain amounts of energy could be added or lost from an atom's potential energy state. So let's consider this. Consider a horizontal string fixed at one end. But allowed to vibrate at the other end. So I've got a little device here that's going to vibrate the string, and it's fixed at this end. Okay, and it's fixed at this end. Let's say the length of the string is 2 meters. Let's say that the speed of a wave that can be produced on this string is 40 meters per second. Okay, and by the way, what determines how fast a wave can travel on that string? Yeah. What's going to determine how fast a wave can travel on that string? Think about a guitar string. How do I increase the amount of energy on a guitar string? Or how do I increase the amount of, well, how do I want to say that? How do I increase the velocity with which a wave can travel on a guitar string?
How tight the cord is.
Yeah, how much I tighten it, right? I can pluck it harder and harder and harder, but the wave is still only going to travel a certain velocity if it's at a certain tension. Okay, so the tension in the string is going to be one thing. If I increase the tension, I'm going to increase the velocity on the string. The other thing is also going to be the material that the string is made out of.
Okay? It should be obvious that on a piece of twine, if this was a piece of twine, the wave's not going to be able to travel as fast as it is on a guitar string. The guitar string's got a lot more intactness to it. It's a lot more solid than this is, right? And so a string is only going to allow a certain velocity, and we're just going to say that whatever this physical system is, it's going to allow a speed of the wave at 40 meters per second. Okay? And so if I say that we have a frequency of 10 hertz, if I say that we have a frequency of 10 hertz, okay, we remember that wavelength equals the speed of the wave divided by the frequency. So I can divide the speed of the wave by the frequency of 10 hertz, 10 waves per second, and I can find out that the wavelength of that wave should be 4 meters. So I'm going to redraw this over here. And I'm going to say that I have, what part of a wave would this be? What part of one wave would this be? Not about half a wave. That's half a wave, okay? Okay? So, this is half a wave. Okay? Notice that it looks like half a wave. This means that since this is 2 meters, right? The length of the string is 2 meters, and my wave is 4 meters, the full wave must have that length. Okay? The full wave must have twice that length. Okay, so that would be a full wave. But if the string is only half of the wave, how do we get a full wave? Well, one of the things that you would need to know is that when wave hits one end of a string, it's reflected in an inverted form. Okay, so when a wave like this hits this fixed point here, this fixed point makes it so that the wave gets reflected back in an inverted form. And that literally completes the wave. Okay, so half of the wave down, half of the wave back completes that wave. And it's only going to happen if my frequency is 10 hertz. Not 11 hertz, not 12 hertz, not 9 hertz, not 8 hertz. In this system, it's only going to happen if my frequency is 10 hertz, 10 beats per second. Okay? Now, when the reflected wave gets back to the vibrating end, it's re-reflected back in the other direction. Okay? When it gets back here, it hits this end, and that reflected wave gets reflected back this way again. But at the same time, another wave comes in from the vibration. Okay? Another wave comes in from the vibration at the same time and adds to it. And if my system would allow it, it would increase the amplitude. Okay? It would increase the amplitude. The system won't allow it, so this is going to be as high as my wave gets. But every time this comes back, it meets another wave and adds to it. What would happen if my frequency was 9 hertz? Where would this wave be, this reflected wave be, by the time my next wave came in?
Let's say it wouldn't be all the way complete.
Actually, it would be past complete. I'm only going 9 per second now.
You almost starting.
Oh.
So my reflected wave got past it, and then I get the next wave coming in. And it's not going to add to anything. It's going to destroy it. So every frequency that I have here that's not 10 is going to destroy this wave. So for this system, for this wavelength, for this system, for this wavelength, I only have one frequency that works. In other words, I only have one amount of energy I can shake this string with that actually works. Every other amount of energy that I apply here in shaking this string is going to cause this wave to be destroyed. Okay? If we look at the vibration of the string, because of the way the reflected waves add together with the new waves, the wave pattern looks like it's standing still. And I'll show you a video of this next time. And we call that a standing wave. For this system, we only get this standing wave if the frequency of the wave is exactly 10 hertz. If it was 9 or 11, the reflected waves would not get back to the point of origin at the same time to add to the next wave, and the reflected wave would destroy the new wave. And what you would see in a video of something like this is that the string actually becomes very chaotic and it doesn't have nice uniform waves. It becomes very chaotic and it doesn't actually have individual waves that you can see. The frequency of this wave is called the fundamental frequency, or the first harmonic for this system. Okay? Whatever that is. What is it that determines the speed of the wave and thus the frequency and wavelength causing the standing wave? We already said it's going to be the tension in the string and the material that the string is made out of, right? Now, if the frequency is increased to 20 hertz, notice what happens. I complete a complete wave in that amount of time. How does that compare to the length of the string? It's the same. Okay, so what that means then is at 20 hertz, I will get one complete wave, and the reflection will get back again at exactly the right time to add to the next wave, and it won't destroy it. Okay? This frequency is going to be called the second harmonic of the fundamental frequency. My fundamental wavelength here is 4 meters. The wavelength of my second harmonic is 2 meters. The frequency of my fundamental wave is 10 hertz. The frequency of my second wave is 20 hertz. These two standing waves are only possible because the waves and their reflections add together. For any other frequencies, reflected and new waves will cancel each other out. Now you should be able to make a prediction. What frequency will provide the next standing wave? $10, $20, 30. Okay, 30 hertz. Okay, and that will look like this. I will be able to complete 1.5 waves with that frequency. And I will again be able to have a standing wave that won't destroy itself. Okay? And now notice my string is 2 meters in length, right? My wavelength here is going to be 2/3 of that, right? So 2/3 of 2 is going to be 1.33 meters. So I can figure out what the wavelength is going to be. So for any string system like this, my primary frequency or wavelength is going to be whatever it is, and that will be twice the length of the string. And my next wavelength will be the fraction of that wavelength where I have the denominator increasing by 1. So 1, 1/2, 1/3, 1/4. So for my fourth harmonic, the wavelength would be 0.5 meters. Okay? So these freestanding waves are only possible because the wave and the reflections add together. For any other frequencies, they will cancel each other out. Hopefully you can see that we can keep doing this indefinitely, and only by adding amounts of energy that give the right frequency will you create a standing wave. And its features and it is the features of the system that determine what those frequencies will be. So if you did this up to 6 times, you would have 3 complete waves. Or 6 half waves. The 6th harmonic would be 0.67 meters, and the frequency would be 60 hertz. Okay? The motion of each of these different waves is called a mode. There are numerous modes that can be produced, but again, they're all restricted by the conditions. Also notice how the frequency increases. 1, 2, 3 multiples, sequential multiples of the fundamental, and the wavelength decreases by sequential fractions of the wavelength. Okay, now, thinking about energy levels. What if my first energy level represented the lowest energy wave that I could produce related to that electron's wave motion? What if I wanted to kick it up to its second energy level? Okay, now I'm not thinking about motion in a circle around this. I'm thinking about this 3-dimensional wave, and don't even try to visualize this because it'll just destroy your mind. Okay? I'm trying to think about this 3-dimensional wave that's more complex, but it's the next wave that I can get by adding a certain amount of energy to it. And you're starting to get the idea that the observations that we made dictated that whatever this system is, it's based on wave motion, and it's not based on translational motion. Okay? So hopefully we've kind of built a case for this as we've gone along and done it in a way that hasn't too completely confused you. But if you understand this idea that to get to the next wave that I can have, that it requires a specific frequency, you're starting to understand that if I drop back down to this energy level, I change the motion of this wave to the motion of this wave. This wave requires less energy, and the rest of the energy gets emitted as an electromagnetic ray. Okay, so we'll continue this. Okay. I hope this is at least a little interesting too, other than just difficult. And obviously, you're not going to have to learn anything about wave functions and things like that. But if you go on in chemistry, or if you go to higher levels of chemistry in college, you'll have to learn a lot of calculus and go through a terrible class called physical chemistry that requires you to know high-level calculus.
like it very much.
Nobody does, it's hard. Well, but the thing about it is, once you grasp it and have it under your belt, then you can rule the world. But I didn't figure that out until it was too late in life.
Thank you.
Uh-huh.